We've had all the statistics ideas, but you just haven't learned how to use them so far. So the formula for the correlation coefficient is the sum from I equals 1 to n of z sub x sub I times z sub y sub I divided by n. How many got that? So you haven't memorized the formulas, so I don't see enough hands right here. Memorize the formulas. Don't, like, in order to understand what I'm telling you about, you need to understand the formulas, you need to have them memorized. It's like a soap opera. Anybody ever watched a soap opera in here? For the first time, somebody's watching a soap opera and you sit down and they're watching a soap opera. What's the first question? People are talking to each other at the soap opera and they're saying stuff like, they're standing there with glasses of wine at some dinner party or some cocktail party. One of them said, I went in the room to put my coat in the bedroom there where the coats are being left, and I found Bob and Alice in bed together. And what is the first question people ask when they start watching this soap opera? What do they say? Who's Bob and Alice, right? Because how do you know what that means? Maybe they're 1 and 2 and they were brought by one of the guests and they put them into bed there with coats, you know. Maybe they're 31 and 32 and they're brother and sister, right? Maybe he's the boss of her husband. All these things mean different things in the soap opera. You need to know who the people are to understand the soap opera. That's the first question you ask is, the people are gossiping about other people. You say, who are the characters? So you need to know who the characters are. And this is one of our characters, is correlation coefficient. All right, the predicted equation for predicting y from x is z hat yi equals rxy z sub x sub I. This is the first formula on that page 7. This is the second formula on the page 7. That's 2 equations. I'm going to give you the third. And that's really it that's on that page that you need to understand. So by all means memorize them. The variance of the residuals, s squared y minus y hat, is equal to 1 minus r squared xy. That's what you have to pay after you get r squared as your discount. 1 minus r squared is the proportion you still have to pay times the original variance. So when you're predicting y from x, you get r squared off. That means you still have to pay 1 minus r squared times the original cost. That's the original variance. So that's the third of the 3. Now the standard error of the regression is just the square root of that. So sy minus y hat is the square root of s squared y minus y hat. And so taking the standard deviation or the standard value is just taking the square root of the squared value. And so those are the equations. How many got this one right here, the prediction equation? Okay, so not enough. Want to memorize these equations. How do you do it? Put them on 3x5 cards. Write the regression equation predicting y from x on one side and write the equation on the other side. And all you need to do is know the z-score and the correlation, and you can compute the z-score of the prediction. Now the husband-wife IQ correlation is 0.6, the means are 100, standard deviations are 15. This correlation is in fact what it is empirically, so that's an empirical fact. These are empirical facts also. It's bivariate normal, that's an empirical fact. What do we mean by bivariate normal distribution? We mean that it's normal no matter how you look at it. So imagine I have some dough, I go over to Trader Joe's or someplace, I buy some pizza dough maybe, or some other kind of dough. Make some dough, get a dough about the size of a football, even though it's basketball season, right? It's March Madness right now. Today the NCAA games are being played. You go from 64 teams down to 32 teams in a couple days, then it'll be down to 16 in a couple more days. Right now the NCAA wrestling championships are going on. I don't know how many wrestlers are left. Maybe they've wrestled a couple times. It's down to 32 or something people still in the tournament. So we got this dough, even though it's football size, even though it's basketball season and wrestling season, we got this football piece of dough. I'm going to form it to make kind of a normal distribution. I'm going to put it on the XY coordinates. Now I'd stick it here, but it would fall off. Well, maybe I'll try. Since it's invisible, maybe it'll stay. So I got this football shaped piece of dough that's on there, and we make it normally distributed, as seen from all directions. If I look from X, it's normally distributed. If I look from Y, it's normally distributed. And this is your old friend, the normal distribution. And your question in A was to draw the normal distribution of husbands' IQs. And so the husbands' IQs have a mean of 100. Well, let's just remind ourselves our standard normal distribution. -2, -1, 1, and 2. 0.34, 0.34, 0.135, 0.025, 0.135, 0.025. Those are the areas under the normal curve. We put the mean at 0, so 100. We add 15, we get to 115. We've done this before. 130 corresponds to a z-score of 2. 115 corresponds to a z-score of 1. We subtract 15. That takes us to 85. Subtract another 15, takes us to 70. So we know that husbands, if they have a mean of 100 and a standard deviation of 15, and it's normally distributed, we know 68% of all the husbands in the world have IQs between 85 and 115, and 95% of them have IQs between 70 and 130, and 2.5% have IQs above 130, and so on. Any questions about that? That you already know. Everybody knows that, right? Any question about that? So that's the answer to A there. Now we got this normal distribution. When we look at it from the X direction, this is what we're seeing. Normal distribution with a mean of 100 and a standard deviation of 15. So we've got this bivariate normal curve. Now if we look at it from the Y direction, it also looks like normal with a mean of 100 and a standard deviation of 15. So that's also normal distribution. But if we looked at it from this direction, it also looks normal. And if we cut into it anywhere, so we slice into it, and then push it aside, so I take a knife, if I put it here, I could cut into it, push it out, and look at it from the edge, it has a normal distribution as seen from the edge, from this side, but the variance is less here than the variance as seen from this edge. So the higher the correlation, the lower this variance is of residuals, of what's left over. Now what is this distribution right here? Well, if the wife has an IQ of 130, this is the distribution of husband's IQs, given you know the wife's IQ is 130. So that's the distribution of Y, given you know X, and that X is 130. So when we cut into that distribution and look at it that way, now if we conditioned on the wife's IQ being 100, you also have a distribution, but it has a mean of 100. What's the mean of this distribution? Well, predict the husband's IQ if X equals 130. To do that, we need this formula, the prediction equation. In order to do this problem, you need to have memorized that equation. So not memorizing the equation makes you done really fast at the beginning of the quiz here. So you start off really fast. Memorizing the equation means spending a half an hour going through the equations. People, I've discovered, college students can memorize, you know, the equations on those 2 pages of the sheet in a half an hour if they put them on cards and go through and simply write them down enough times till they get it right. So by all means, go ahead and do that if you haven't done that already. We've got these 3 equations for page 7. These are the new ones we've had since the midterm. All right, so we need this equation in order to find the answer to B, and the equation is y hat I minus 100 divided by 15 is equal to 0.6 times the z-score of X. So I'm just substituting in what I know. This is the z-score of the prediction. This is the correlation coefficient, was given to us as 0.6. And the z-score of X was given to us as 130. So we have 130 minus 100 divided by 15. All right, any questions about that? So you should already know how to do that. That was the kind of problems we're doing for homework. Homework number 14 and that we did last time. Now we have 15 on both sides, multiplied by 15. We get y hat minus 100 equals 0.6 times 130 minus 100 is 30. 0.6 times 30 is 18, so we have y hat is equal to 118. All right, so I multiplied through by 15. I multiplied 0.6 times 30. I added 100 to both sides, and I get y hat is equal to 118. What does that 118 represent? If you knew that the wife's IQ is 130, what do you predict the husband's IQ is?
118.
118. Then it says, find the mean value of the husbands whose wives have IQ of 130. So if you took all the wives whose IQs are 130, what's the mean of all their husbands' IQs? 118. So basically, C is just asking you the same question as B, and the answer is also 118. So the answer to B is 118. And then realize that this is the same. That's basically what it is. It's guaranteed to be the same in a bivariate normal distribution, and it's on average, it's a good guess of what it is if you don't know that distribution. So that's the predicted value, y hat I, given you know what x is a linear function of x, and the mean value of y, given you know x, is the same as y hat, and that's true and definitely true in a bivariate normal distribution. And it says find the standard error in this case. Well, to do that, you need to find the variance of the residual, and so that's equal to 1 minus 0.6 squared times 225. Why 225? Because the standard deviation is 15, so the variance is 225. 0.6 is squared is 0.36, so you get 36% off at the mall, right? 36% off the mall means you still have to pay 64, so it's 0.64 times 225. That's 144. I choose numbers that are nice to you. 144 is a gross. That's perfect square. You can take the square root of that. So that means that the square root of 144 is 12. So the answer to this question is 12. Sy minus y hat is equal to 12. So the standard deviation of the husband's IQs is, the mean is 118, and the standard deviation in this case, Sy minus y hat, is equal to 12. Now it would have been 115 if we didn't know anything about x. But given we know x, we now can say, well, we know that the wife has a high IQ. You can guess that the husband's IQ is 118. The mean value is 118 with a standard deviation of 12. All right? So that's how that works. Yes?
Where is the 225 from?
Where did what?
The 225?
The 225 is the, here's the equation. We take the squared value of the correlation. We take 1 minus it. This is our discount, so that means that's what we still have left. That was the original cost of playing the variance game. The variance. The standard deviation is 15. So that means that the variance, S squared y, is equal to 15 times 15, and that's equal to 225. All right? So the variance is the square. If you know the standard deviation, you square it to get the variance. If you know the variance, you take the square root of it to get the standard deviation, so you can go back and forth. All right? Other questions? So that's where the 225 came from. So I applied this formula, then I took the square root of it to get the standard deviation. So these formulas are ones that we had last time right here, and now I'm just showing you how you could use them. And so the answer to the standard deviation is 12. Answer to the mean value is 118. Then it says, draw the distribution of the husband's IQs. So whereas the original distribution of husbands' IQs, or wives, I guess we have, oh yeah, I guess I meant to really, I wanted husbands up here. Husbands' let's put husbands up here. And wives, I guess I changed my mind here about predicting from X to Y. Women have two X chromosomes, right? And men have an XY chromosome, so thought I would put the husbands on the ordinate here and predict the husband's IQs. Well, it'll work either way, but for this problem. So the husband's IQs have a mean of 100 and a standard deviation of 15, but given you know the wife's IQ is 130, this is the distribution, a mean of 118 and a standard deviation of 12. So we can do that in the same kind of way. We start with our standard normal distribution, so just draw your standard normal distribution. 0, 1, 2, minus 1, minus 2, 0.34, 0.135, 0.025, 0.135, 0.025. Now, corresponding to the mean, what's the mean of the husband's IQs now? Given the wife has an IQ of 130?
118.
118. So we'll put 118 here. And what's the standard deviation of their IQs now that we know the wife has an IQ of 130? So now that we know that the wife has an IQ of 130, we know that the mean is 118, and what's the standard deviation? We calculated it from the residuals, right? Standard deviation of the residuals, also known as the standard error of regression, also known as the standard deviation of y given you know x. And so that's 12. Adding 12 to 118, we get to 130. So what percent of the husbands are going to have IQs of greater than 130? 0.135 plus 0.025. So the proportion of men, of husbands, of women whose IQs are 130, who have IQs above 130, is 16%. 0.135 plus 0.025. 16.16 or 16%. So that's the distribution of the IQs of husbands, of wives whose IQs are 130. So the question is, why do so few women with IQ 130 have husbands as high as they? Is that because they're worried about self-esteem? Is that because they don't want to be challenged by their husbands? No, the answer is because there's so few men with high IQs.
No.
Very few men have IQs as high as they do, because once they're in the top 2.5%, there's only 2.5% of the men have IQs like that. And for them women to marry husbands whose IQs are as high as they are, they have to get that whole 2.5%, don't they? And believe it or not, people marry for other reasons besides IQ. I know it's hard to believe. What else do they marry for? What would a high IQ woman marry for besides IQ? Wealth? Personality? Figure? Right? Now people are saying, what? Other things? Right? Religion? Compatibility? Huh? Okay, so these women are marrying men for their looks or some other thing. So they're not getting there. The correlation here is only 0.6. It's not 1. So this is one of the paradoxes that comes from statistics. You don't need to make up a story. If you read a magazine, this is the basis for a magazine article. There have been articles like this written. Now it works the other way too. Why is it so many, really good-looking actors, when you meet their wives, the wives aren't as good-looking as the actors? I know you're going to think of some exceptions, but think of Julia Roberts when she was married to Lyle Lovett, or, cases like that, right? You're going to think of Brad Pitt, and, I don't know. They're pretty good-looking, both of them, but if you look at the average looks of once you pick somebody who's really good-looking, on average, their spouse isn't as good-looking as they are. So if it's the actor, the wife isn't as good-looking. If it's the actress, their husbands aren't as good-looking. And you say, oh, well, she married him because he's rich and powerful, or because he's a rock star, or some other reason. All right, questions about how to do these problems? Any questions about it? First thing you have to do is memorize these three equations and then figure out how to use them. This is the equation for predicting y from x. And you will switch x and y when you're predicting x from y. So you can use a correlation to predict from x to y or from y to x. And keep in mind, correlation is the tool of the devil when it's used to argue for causation. So we're going to be using these statistics now in order to talk about heredity and environment and IQ. We haven't really talked about what IQ is, but we've used it as an example already for the statistics. But we need to know the statistics in order to understand the content of IQ. Any questions before we erase this right here? I'll leave that up for a little bit. We'll work over here on this, on these sheets. All right, so I told you last time the story about Darwin, and here's a cousin of Darwin named Francis Galton. How many of you had heard of Charles Darwin before this class? Presumably they tell you about it in high school, some biology course or science course in grammar school. And Darwin's theory of evolution, and all the species are basically descended from one animal. Well, Galton is, Charles Darwin and Francis Galton had the same grandfather, Erasmus Darwin, that I was telling you about last time, that had the theory of evolution that we don't agree with anymore these days. The one I was trying to tell you about the last governor of California as my illustration of the story. Francis Galton, also like Charles Darwin, traveled. He went to Africa, he had adventures, wrote books about his travels. And he came home and he read Darwin's book. So Darwin went on his travels and wrote his book and his theory of evolution. And Galton got really interested in these questions and he began doing some research, trying to understand better what it was that his cousin Charles Darwin was writing about. And they thought that genetics, the material of genetic inheritance was in the blood. People talk about blood, about what percent blood of this race or that race you are. It's an old-fashioned idea about genetics, blood mixing. It's a wrong theory, but that was a theory they had at the time, and they tried things like this. They got a brown rabbit and a white rabbit, and they took some blood from the brown rabbit, injected it into the white rabbit, see if they could, get a spotted rabbit or a light brown rabbit, things like that. They killed a lot of rabbits that way because they didn't know about blood types. And this is not how genetics is transmitted through the blood. But there's still a lot of language, there's still some laws in some southern states talking about blood mixing and so on. He was also an anthropologist. He's the first quantitative anthropologist. And he did this study. He set up a tent at the World's Fair, and you could pay to go through this tent and be measured. So you'd go to the World's Fair, you'd go to the tent, the measurement tent. And you went in the tent, you'd pay them your price, and they would measure your height, they'd measure your weight, they'd measure your waist, they'd measure your chest, they'd measure your bicep flexed, they'd measure your chest expanded or relaxed, they'd measure your neck. They'd measure how close could two tones be, and you could still tell the difference. So they'd play two notes to you, and they'd say, are those the same tone or two different notes? They'd have you lift weights and tell, okay, is this weight the same as that weight? How close could two weights be? And they'd put two little points on you and touch you on the skin in different places and ask, how close together could 2 points be? And you could tell that it was 2 pins rather than one. If the 2 points get close together, people think they're being poked by just 1 point. And you may do that study. We used to do that as a lab study in perception, laboratory and perception, where they measure how close 2 points be. How much shock could you hang on to before you had to let go? So you'd grab onto 2 electrodes and they'd turn up the dial zzz, until you had to let go of it. Stuff like that. They still have this in some bars, I understand, right? You go in the bar, you put money in, you grab a hold of the 2 handles, it goes zzz, until the guy lets go, and then it says, wimp. You have to put more money in, right? You keep saying wimp, wimp, until you're electrocuted and killed. So that was his deal, is making these measurements, and he measured the heights of fathers and the heights of grown sons. So you had cases where the fathers and sons were both being measured. And he had his table of all these data, and he's looking at the table of data. And the story goes, I don't know if this is a true story, but this is the way the story was told to me. It's in the books. Sometimes these stories are apocryphal, but he's sitting waiting for a train, and he decided to calculate what's the average height of the son, of the adult son, of fathers, depending on how tall the fathers are. So he's drawing his graph. Here's the father's height. And the fathers, he found that the average height of the fathers in those days was 68 inches, and that was the average height of the sons. It helps if you have graph paper, but I'll do the best I can do here. "72 inches, how tall is that?" That's 6 feet, right? 68 inches, that's 5'8". That was average. 66 inches, 64 inches. He found that the standard deviation was about 2 inches. 64 is 5'4". 70 inches, 72 inches. Now, one of the things they had was this blood mixing theory of inheritance. Take a tall person and a short person and you mate them together. If you have a blood mixing theory, what should you get? An average person, right? That's blood mixing. If you take a red flower and a white flower and you crossbreed them, what should you get?
Pink.
I'm going to say pink. If you've had Mendel's laws, you know it's not pink, right? So they didn't know Mendel. Mendel was busy working at the same time, and he sent them his paper. But Darwin and Galton didn't know about Mendel. So if people mate randomly, and that's a pretty good approximation, you're supposed to laugh at that. Think about it when you get home. Anyway, people mate randomly, and that's a pretty good approximation. Within a few generations, everybody should be the same height, according to their blood mixing theory. And this was called regression. Regression to the mean, which was an implication of blood mixing genetics, which is a wrong theory, but that was the prediction they had. And what he did is he looked at 64-inch fathers, and he found that on average, the 64-inch fathers had sons that were on average 66 inches tall. And he said, maybe people are getting taller. And he looked at the 66-inch fathers, and he found that the mean height of the 66-inch fathers was 67 inches. Again, it looks like the people are getting taller. And he took the 68-inch fathers, and he found on the average, though, the sons were 68. And he looked at the 70-inch fathers, and he found that on average, the sons were 69, shorter than the fathers. And the 72-inch fathers, and found that on average, the sons were 70 inches tall, shorter than the fathers. And he said, regression to the mean. This is evidence of the blood mixing theory. People are going to all end up the same height because the sons of short fathers are taller than their fathers, and the sons of tall fathers are shorter than their fathers. So he drew this line in, and it gets called the regression line. Because it was regression to the mean. But he had the same data, and so he decided, I'm going to average the data another way. And he looked at the data another way, and he said, how about the sons who are 64 inches tall? What are their fathers like? And he found that on average, if the son was 64 inches, the average, so this line right here is the average height of sons as a function or plotted against the fathers. So that's what that line is. And you notice that the sons, on average, the fathers that are short have sons that are taller than they are. The fathers that are tall have sons that are shorter than they are. Then he did it the other way, and he found that if the son is 64 inches tall, the fathers, on average, were 66 inches tall. And if the sons were 66, the fathers were 67. And if the son was 68, the father was 68. And if the sons were 70, the average father was 69. And if the sons were 72, the average father was 70. And so this line shows the average height of fathers plotted against their sons. And so there's regression to the mean going in two different directions. This is a paradox called Galton's paradox. Why is it a paradox? Well, it'll seem more paradoxical to you maybe with other examples, but it seems like you're saying the sons are taller than the fathers. For short fathers, the sons are taller than the fathers, but for short sons, the fathers are taller than the sons. So the fathers are both shorter than and taller than their sons. And that seems sort of paradoxical, right? And the reason it seems paradoxical is if you think there's one line and one function there, and you can go from x to y and from y to x, then it's paradoxical. But it's not a function, it's statistics. And this paradox is just statistical. And the person who explained the paradox to him was Carl Pearson, who was a student of Galton. And he used the relationship between these two lines to calculate what we now call the Pearson product moment correlation coefficient that you've already learned. So the equation we have for the correlation coefficient, you multiply the z-scores together, that's called the Pearson product moment correlation. That's the product of moments. And so Pearson, who was a student of Galton, he deduced RXY and explained this to Galton and said it has nothing to do with your genetics theory. It has nothing to do with blood mixing. It only has to do with the fact that things aren't perfectly correlated. So regression to the mean, and so the prediction equation is also called the regression equation. The word regression is left over from this old theory of blood mixing, a wrong theory of genetics. So sometimes you'll see the word regression in that context. Now it just refers to the fact that the prediction is always regress to the mean because the correlation is less than perfect. So if you're predicting from x to y, you will always go toward the mean of y. And if you're predicting from y to x, you'll always regress toward the mean of x. If you knew nothing, the best guess is the mean of whatever it is you're trying to predict. And then you go less extreme. How much less extreme depends on the correlation. If the correlation is 1, then you predict y is as extreme as x. And if the correlation is less than 1, to the extent it's less, you go more and more regression to the mean. And so regression now has a purely statistical interpretation. But it has this leftover in the history of biology and genetics and, as we'll see in a little bit, eugenics. All right, any questions about that so far? So this should look fairly familiar to you. This is basically the correlation between height of father. Let x be equal to the height of father, an adult, and y equal the height of the son. And again, we're talking about an adult height, so we're not measuring sons of all different ages. So we're measuring the son's adult height. The correlation between x and y, RXY, is 0.5. Same as the correlation in IQ between fathers and sons, mothers and daughters, mothers and sons, mothers and daughters. All four of those correlations Mother, son, mother, daughter, father, son, father, daughter. Correlations in height are 0.5. Correlations in IQ are 0.5. Right? 0.5 correlation. How big is it? 25% of the variance. Here's one of the findings that Galton had. He looked at eminence and criminality, and his results were pretty much the same kind of finding. What's his definition of eminence or fame? Well, in those days they had a book called Who's Who. Today maybe it's kind of like Wikipedia, I don't know, although Wikipedia keeps growing and I'm even listed in Wikipedia. Of course I was in the Who's Who too. Well, I guess it's because I'm famous. All right. You guys don't realize it yet, but yeah. All right, so you look at eminence. Who's listed in the Who's Who? Well, in the old days, you know, you'd list people because they're members of royal families, because they're the heads of banks, because they're politicians, because they're famous for some other kind of thing, and they end up in the Who's Who. In other words, who is it that people might be interested in knowing who they are? So, Michael Jackson, you know, would be in there. Boehner would be in there. You know, Bill Gates would be in there. Robert Koch would be in there. Koch brothers would be in there. Studies of eminence, people that are famous for something. And if you take 100 eminent men, how many of them have sons? In other words, if they're listed in Who's Who, how many of them have sons that are listed in Who's Who? And it turned out that out of 100 eminent men, on average, there were about 48 eminent sons. If you take 100 men who are not listed in the Who's Who, you just choose a bunch of people not listed in the Who's Who, you know, on average you have less than one, averages out to 0, because less than 1% of the population is listed in the Who's Who. Same for criminals. So if you have people that are in jail, 100 people that are in jail, you find 48 sons of these people that are in jail have sons that are in jail. And on average, 100 people that aren't in jail don't produce, on average, a person in jail. Of course, that was before the United States when we started putting everybody in jail, practically. We're the most incarcerated nation in the world. Here's a quote from Galton. I think we got it on there. Trying to get away from that. If a man is gifted with vast intellectual ability, eagerness to work, and power of working, I cannot comprehend how such a man should be repressed. And then he coined the term eugenics. He says, if you want better people, breed them. We know how to breed faster racehorses. And you want better people, you need to breed them. So the idea of eugenics was the idea of breeding better people. And as you know, that's a fairly controversial idea. We'll come back to that more later and talk about different political people that have had. Do you want more time with that quote? There's a quote by Sir Francis Galton, the cousin of Darwin. Now here's an idea that they didn't know about. Unbeknownst to them, there was a monk working in Brunn, now called Brno, in the Czech, now what's now the Czech Republic. It was part of the Austro-Hungarian Empire, and I want to go over this with you a little bit. See if we make it a little bit smaller here, because the figure is a little bit confusing, and it appears in some editions in the chapter on in biological psychology, chapter 3, but for some of you it may appear in the developmental chapter or elsewhere. Now, I have a feeling that Cowlett had trouble communicating with his artist. You know, he drew a sketch of what he wanted, and then he tried to tell the artist what he wanted. My guess is he sent a note saying to the artist, I want you to use blue and pink for the genes from the father and the mother. Now, if you were going to choose blue and pink, which would go with the father? Blue or pink? And which would go with the mother? Pink, right? So what did they do? Gene from mother, blue. Gene from father, pink. And he probably said, I want you to use squares and circles for the dominant or recessive genes. Now, which would you think would be dominant? A square, which has 4 corners, or a triangle, which has 3? I would have made the square be dominant over the triangle, because it's got more corners, right? Or something. But they decided that the dominant gene is going to be the triangle and the recessive. And they're looking at a single Mendelian trait. Tongue curling. How many of you can curl your tongue? Yeah? Tongue curlers? How many cannot curl your tongue? Right? So that's recessive. Here he is curling his tongue. So let's go over the basic ideas of Mendelian genetics here. You probably had this in some course someplace, but here's the idea. You get humans have pairs of chromosomes. You get one set of chromosomes from your mother and one set of chromosomes from your father. This is called sexual reproduction. It was discovered by plants a long time ago. Your parents probably told you about birds and bees and flowers, right? And the flowers are basically sex organs, right? Because, yeah, they're sex organs. They have eggs and they have sperm in them. And the sperm is the pollen, and you can crossbreed plants by taking pollen from one plant and putting it on the little collection, the sex organs of the other plant, and so you can breed plants together that way. And plants discovered sex, and other animals have been taking advantage of it ever since. You get half your genes from either parent, and so you have 2 copies of each gene, and genes come in alleles. And alleles might be in what's known as the dominant form or what's known as the recessive form. So tongue curling is dominant, and the non-curling is the recessive form of the gene. All right? And so for each pair of genes, well, let's just look at the relationship between the genotype and the phenotype. So here's Gregor Mendel, and he's working in Brunn. He's a monk. He's working as just a scientist, but he's, a member of a monastic order. He has a little garden plot, like half the size of this classroom. He's raising his pea plants. He gets out there, he crossbreeds them. You know, he has to keep them from flowers from opening up and sending their pollen to the wind so that they breed randomly. And he comes up with this theory. Now, if you have 2 recessives, form, that's called homozygous recessive. The word homo refers to the same. So a homosexual wants to have sex with a member of the same gender, and a heterosexual, that means different, wants to have sex with a member of the opposite gender. So homozygous means the eggs, zygote meaning egg, homozygous means the eggs are the same, or the genes in this case are the same. So homozygous recessive means 2 genes that are both recessive. The genotype is what the genes are, the phenotype is how it looks. So the person is going to have the recessive phenotype. So if both your genes say you can't curl your tongue, then you can't curl your tongue. So the phenotype is what you can actually do and how it looks, you know. But I can do it. Okay, bye. All right, so the person can't curl their tongue. Now, if you're heterozygous with the recessive and dominant, so you have one, so you have either the recessive from your mother or the recessive from your father and the dominant from the other parent, then you're going to have the dominant. And if you're homozygous recessive this way, or homozygous recessive the other, homozygous with a recessive and a dominant, heterozygous with a recessive dominant or dominant recessive. Now if you're homozygous dominant, which means you have dominant from the mother and dominant from the father, then you're going to have the dominant. And so that's what this diagram is trying to show you. Now, if you have either from your mother the dominant with a recessive from the father, pink, or you have recessive from the mother but dominant, the triangle, pink, from your mother, you're heterozygous. Or if you're homozygous dominant, so that means the mother, blue, and the father, pink, of dominant, any of these three cases, you can curl your tongue. And so I'm drawing this little bracket around it to show that these are the three cases where the guy can curl his tongue. But only in the case where it's homozygous recessive can you not curl your tongue. All right. So let's ask you a few questions about the milkman. If your parents can curl their tongues, does that mean you better be able to curl your tongue? No, because they could be, your parents could be heterozygous and be able to curl their tongue, and they could have, so let's look at what happens if you have heterozygous parents. So, this is the gene you get from your mother. This is the gene you get from the father. Right? The mother can produce a recessive or a dominant. The father can produce a recessive or a dominant. Both of them can curl their tongue because they're heterozygous, right? But you could get a recessive, in which case you would not be able to curl your tongue. But in these three cases, either dominant recessive or dominant recessive or dominant dominant, you would be able. So if the parents are both able to curl their tongue and the kids can't, that's perfectly reasonable, isn't it? How about if both parents can't curl their tongue and you can curl your tongue?
You're in trouble.
Then we have to go back to Arnold Schwarzenegger again, right? Which by now you should be getting the joke, right? Oh, wait a minute, it's the other way around. If Maria Shriver were to have children, okay, so if the children, if the children of two parents that can't curl their tongue, if the parents can't curl their tongue, we know what? They're homozygous recessive, right? So they both, and two recessive people can't have a child that can curl their tongue. Brown and blue eyes, it's not exactly a single Mendelian gene, but approximately. So brown eyes, brown is dominant over blue. If a person has two blue-eyed parents, that means that they, in theory, that they both have two recessive. So two blue-eyed parents should only have blue-eyed children, but a blue-eyed parent with a brown-eyed parent could have blue or brown-eyed children, I mean. Two brown-eyed parents could have a blue-eyed child because they could be, right? And so on. So this is basically the idea of Mendelian genetics. Here's one of the first experiments Mendel did, is he bred flowers so that he had only white flowers and no pink flowers or no red flowers being grown. So these are pea plants that are all white. So he breeds back only white and he has all reds. And he breeds within the whites with whites and the reds with reds, and if there's ever a red flower comes out here, he gets rid of those plants until he thinks that he has, if he breeds two of these together, he gets all white, and he now thinks he has homozygous So they're white, white. So these are all white, white. And these are all red. If I crossbreed these, what do I get?
Depends on who's dominant.
All red and all white. I breed them together, what do you get?
I don't know, is there color on
Who's dominant?
Red is dominant.
Well, then you get red.
Yeah, so they're all red because the mother can give a white or a white, and the father can give a red or a red, and so they're all white, red, white, red, white, red, white, red, all red. Not all pink. That's the blood mixing theory. So if Darwin and Galton had been paying attention to Mendel, which they weren't aware of it, but Mendel was working about the same time. He did send his paper to them, they say, and that maybe they looked at it and didn't get the mathematics. Now if I breed two of these together, what do we get? So let's take, this is the first generation. So this is sometimes called the first generation. Then if you breed two of those, first generation, the all reds together, what do you get?
75% right.
Yeah, so now we're going to have a white or a red. So every one of these, when I breed, is going to either give you white or red, or a white or a red. So now we're going to have white, 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 red, red, white, or red, red. 3/4 of these are going to be red. So these are red. And you're going to get basically the 3-to-1. This is one of the Mendelian ratios. The 3-to-1 ratio is one of the Mendelian ratios. What if I take one of these reds and I breed it with one of these reds? What do you get? All reds. What if you take one of these whites and you breed it with one of these? What do you get? 50%. So that's another Mendelian ratio. If you breed this with this, you get 50% reds and 50% whites. And so you should be able to predict all sorts of ratios, and that was the whole business of Mendelian genetics. And according to Mendelian genetics, the variance doesn't go away. So the main problem they had, Mendelian genetics allows Darwin's theory to work for evolution. But Darwin's theory doesn't work because, according to Darwin, all the variance goes away, but his theory requires variance, right? For natural selection to work, you cannot average everything together and have all the birds end up with exactly the same beak length. You got to have variability for inheritance to work. You got to have natural selection working on the characteristics. But the variability doesn't go away according, all these genes stay there except for natural selection according to Mendel's genetics. So Mendelian genetics is just what Darwin needed, but he didn't actually have. So kind of an interesting fact about that. Any questions about Mendel's genetics? So you should be able to find that in the textbook, somewhere in the book, maybe in chapter 3. Let's get into intelligence. So